Good morning, all of you. Hello. Very
Yeah,
good morning.
we are able to listen, sir.
Listen,
Yeah,
okay.
you can just carry on.
Hi, Dr. Lakshmi Padaya, faculty in the Department of Civil Engineering of VKIT Bengaluru, welcomes you on to all fourth day webinar on design and construction of steel structures. I welcome today's speaker, Mrs. Nibedita Dey from INSDAG for today's webinar, which is on 9th June 2024 noon. I also welcome Dr. C.S. Shashi Kumar, HOD of Civil Engineering, VKIT, and all the faculty members of the Civil Engineering Department and all participants for today's webinar. Now it's my privilege to introduce today's speaker, Ms. Nibedita Dey, who is graduated from Jalpaiguri Govt Engineering College, West Bengal in the year 2002 and also obtained master degree in structural engineering from Jadavpur University, Kolkata in the year 2004. She worked as a structural engineer in different projects of Steel and RCC in Design Consultancy firm like Development Architect Private Ltd, Steel Plus Limited, Thyssen Krup Industries Private Ltd, and PK Dey and Associates. She also worked as lecturer for teaching analysis of design and structures. Mrs. Dey joined INSDAG in the year 2011 and at present she is working as manager, civil and structural engineering. She is responsible for technical promotion activities, R&D projects and publications. I also welcome Mr. A.K. Samantha, General Manager, Mechanical INSDAG. I request you, sir, to speak few words about today's forenoon session. Sir, over to Samantha.
Sir, Samantha, sir.
Yes, sir.
Yeah, can you please speak a few words about
today's?
Good morning, everybody. I am very happy and pleased to note that exactly we are progressing smoothly through this 5 days refresher courses. Consisting of 10 lectures, we have completed 6 lectures till yesterday, and today another 2 are scheduled. And just now, my colleague Ms. Nibedita Dey, she is going to present on earthquake resistance design and of structures. So I know she is very expert, and she did her post graduation from famous Jadavpur University, Kolkata. So now, sir, if everybody is ready, I would like to request her to start her presentation. So we are starting now, sir.
Thank you, sir. Thank you. Sir, now.
Okay, Nibedita, you can start now.
Sir, just a minute, sir. We will complete formalities, please.
Hello, sir.
Yeah.
Now I request Dr. Shashi Kumar, Professor in HOD of Civil Engineering, to welcome the speaker, today's speaker.
Actually, today we have a session on advances in seismic design of steel structures. I think, Madam, there was a time we felt that all the designs of the steel structure should be designed for wind loads only because of their lightweight. And now the codes are changing, and there is a now shift. Not, I think, drastically. I feel there is certain clauses that are being incorporated in the codes regarding detailing and others. I think Madam will throw light on it and also advances in the seismic design. And on behalf of VIVEKANANDA Institute of Technology, I would like to welcome her for this webinar. And I would also like to thank her for accepting the invitation for delivering the lecture. Also, I would like to welcome all the participants for this session. Hope they will enjoy this session as well. Thank you.
Okay, Nibedita, now I think you can start.
Now over to Nibedita Dey, today's speaker.
You share the screen.
Madam.
Sir, she is taking up. I think all others, please go on mute.
Is the screen visible to everybody?
Yes, yes. Now try to slide it.
Okay. Is it moving?
Yes,
Yeah.
yes. Yeah. Okay, okay. Now you can
Okay.
start.
Okay. Then I will start. Okay. So, thank you for inviting us in this webinar program. Today's program, I will try to present some issues and challenges and some analysis and design principles regarding earthquake load analysis, and specifically some points regarding the steel structure resisting the earthquake loads. So I will start my presentation. And presentation topic, as you see, that behavior of steel structure in seismic conditions. Mostly I will go through the analysis and design principles and what are the theories behind the analysis of a frame which are going to resist the lateral load of earthquake engineering. In this presentation, the following outline I will follow. First, it will be overview and the stability of structures. Then the failures in earthquake, what we have seen in earlier, some images on the failures and what lessons we have learned studying the failures, and what kind of principles we need to remember during assuming the stability of structure, how our structure will going to act in the loads. Then principles and philosophy of earthquake resistant design, how to determine the earthquake load, what are the method of analysis in seismic loading, and the design of steel frame building for earthquake forces, what are the systems we are using, and last we will try to understand seismic behavior, particularly for some steel sections, and what are the advantages choosing the steel structure for earthquake load. First, I will introduce a little some theories behind the formation of earthquake, how it will occur. Generally, earthquake occurs along the fault lines, cracks in earth crust where tectonic plates meet. They occur where plates are subducting, spreading, and slipping. And it is not predictable when this would happen. As the plates grind together, they get stuck and pressure builds up. Finally, the pressure between the plates is so great that they break loose. In this figure, you can see that when the two plates move between these two, and a seismic wave is generated, and this seismic waves is spreaded, and through the ground it will hit the earth portion underneath the structure. First, it will hit the foundation and it will start some vibration which is transmitted to the structure. The tectonic plates are always slowly moving, but they get stuck at the edges due to friction. When the stress on the edge overcomes the friction, there is an earthquake that releases huge energy in waveforms that travel through the earth crust and cause the shaking. When it can be felt, and that is felt when we understand that it is when it is we are having earthquake. Some past earthquakes, uh, when we faced the damages and loss of lives in these earthquakes, these two biggest major earthquakes in respect of death and damages, we can remember Latur earthquake of 1993, which considered to have occurred in very stable region. And generally we think that earthquake occurs in for some loose soil only, but it has changed the views after the Latur earthquake. It was a very stable zone, but still we felt these major earthquakes. And after the Gujarat earthquake of 2001, many wrong conceptions which were earlier there, that building of U shape, L shape is preferable as the different arms in orthogonal election may be giving stability, it has been proved wrong. And then after the earthquake, people who have analyzed the earthquake effects, then it is felt that steel is most suitable for earthquake, as it has the ductility property. Wood is also, for its lighter weight, it is good for seismic structure to be made in seismic zone, but would not have that property of ductility as compared to steel. Here you can see the damage pictures of two earthquakes. First one is Gujarat earthquake. Magnitude of this earthquake was 7.7, and total toll was over to 20,000, and there was huge injury of 1,60,000, more than 1,60,000, and it lasted about 2 minutes. Several towns and villages were destroyed in this catastrophe. And you can see the total damages. It is a report from Gujarat Earthquake Recovery Program. They have reported that if total damages was amounted of rupees 9900 crores. And the same type of damages we faced after Latur earthquake, which was of magnitude 6.4, and total injuries over 30,000. And several villages have faced massive damages. And it has been proved that even in the low occurrence of earthquakes, structures should have some capacity to resist that should not be damage our lives.
Excuse me, madam, 1 minute. Sir, Samantha sir, can you please go on mute? Yeah,
Yes, sir.
madam, please continue, madam. You had unmuted. I just requested you to mute.
Oh, I want to meet.
Yeah. Mute. Go on mute. Madam, you can start, madam. Thank you.
Okay. Earthquake, after the seismic wave is generated, it causes different type of forces. And what are the forces? That is ground shaking. Another effect, it causes surface structure. In the picture, you can see that due to ground shaking, building may collapse. Even in surface structure, this earth crust has been ruptured, road has been damaged. Liquefaction's effect is there. What is liquefaction? When a loose consolidated sediment soil saturated with water may be turned into liquid for the effect of earthquake, and that time it cannot support the building, so it collapses immediately. The foundation cannot take that load. Then again, tsunami is formed after the earthquake. We have experienced that in 2004 in the near about Andaman in Indian Ocean. The effect of tsunami was the effect of earthquake. Even it can cause fire after a massive earthquake. And also it can cause landslides. So we cannot predict and resist fully all these forces and damages, but we can at least take step to design the building to resist to some extent the damages and collapse of our human built buildings. Here are some pictures of earthquake failures, some steel failures in RC buildings. You can see the failures of corridors. Here you can see the failures in the bracing and the column itself. Here is a total collapse of one story. Here is a failure due to soft story in the ground floor. Here the failures of bracings, and it is totally failure of liquefaction. Here is some more pictures of the failures. We generally, after the earthquake, when we see the failures damages, then we start to study what are the causes of this earthquake, how it can be protected in future. So there is a need of study of earthquake damages. It provides invaluable information of the performances of the real structure under actual earthquakes, It is like a full-scale testing of variety of prototype structures under real earthquake. Each earthquake exposes the inadequacies of the prevalent design of construction, which we can rectify in our future design. It also provides good features of design and construction. And failures in earthquake can happen in many ways due to soil characteristics and depth of foundation, due to the overturning of RC masonry building, due to failure of connecting corridors, due to interaction between masonry and RC building, due to soft and weak story, foundation deficiency, liquefaction, ductility lacking, and also due to failure in the shear walls designed for lateral load. Now, what we can do? If we design all the structures for massive earthquake, then our design may not be economical, because there is no probability of severe earthquake occurring frequently during the life of the structures. So we have to judge when we are designing the structures for any earthquake. To resist such earthquake, which are not very high but create some damages, huge damages. The structure is not collapsed, but we can see the damages which we will be able to repair. So we have to think how we can take steps for both type of design. So we have to ensure elastic behavior under a moderate earthquake, which has a return period equal to life of the structures. Maybe some moderate earthquake may happen some 2 or 3 times or some more times during this life of structure. But a severe earthquake don't have that frequent return period. So we have to prevent collapse under the extreme probable earthquake. We have to allow some damages before the collapse. We have to ensure the ductility property that allows large deformation without collapse, and we have to ensure the ratio between the ultimate deformation at an assumed point of collapse to the deformation at yield point, which is mean the ductility. I will explain more about the ductility in later slides. Another terms we need to understand that hysteric energy dissipation. Hysteric energy dissipation, it is the energy dissipated by inelastic cycle deformation. When earthquake load is acting in the lateral load systems, the structure is, any member is first getting loaded. When it is loaded, it is subjected to some deformation. Like when we are plotting the stress strain curve, when it is loading, some deformation is there. First, sometime it is the member is elastic, that is the linear line it will follow. After sometimes it will reach the yield point, and after yield point, when it is getting loaded again, the curve will be flattened, and at sometimes it will be flat. So again, and in earthquake load is again reversed. At some point load is, if it's right direction, then after sometimes load is in the left direction, that's opposite in the direction. So when the member is getting different unloaded, that means in different side it is loading, then the curve is in the different side. So when it is cycled like this, the area covered by this cycle, it is the energy work done, that is the energy by this inelastic cycle deformation. And this area is very much required for energy dissipations for a lateral load resisting system during the earthquake. And it is given the area within the load deformation curves. It is called the hysteric curve. And for moderate and severe earthquakes, some properties we have to ensure. For moderate earthquake, we need to ensure that the structure, the lateral load resisting system have proper yield strength and elastic stiffness. And for severe earthquake, we have to ensure that it has proper ductility, and all the members and the members which we are assuming to resist a earthquake load, we have hysteric energy dissipation capacity to avoid collapse. Here you can see that in the left figure, figure 1A, it is a ductile and non-ductile behavior. When the members it's not non-ductile, after reaching the yield point, the member get after it collapse. But in the ductile property, the member before it collapse load, the long strain is there. It is deformed, but it doesn't break or collapse. So this property is very much required for earthquake resisting members. And figure 1B, it is showing the pore energy dissipation capacity, like the cycle lines are very much close to one another. So the area under this full curve is lesser. And in the second figure 1C, the area under this hysteretic curve is more. That means it has good energy dissipation capacity. Earthquake generates the energy, and that energy has to be dissipated by the member resisting the earthquake loads. So good energy dissipation capacity is required. And one more thing, these all curves are taken earlier from some different experimental results in some institutes. Then it is included in the literature. Like figure 1B shows the pore energy dissipation capacity, and the structure is likely to collapse due to low cycle fatigue. And for this, there is a strength and stiffness degradation under the repeated inelastic cycle, and it is called low cycle fatigue. And it is to be ensured the structure is able to dissipate a large amount of hysteretic energy in each cycle that can minimize low cycle fatigue effect. Figure 1C, for this, we can tell that thicker section, which is lesser chance of buckling in steel structure, it shows the good ductility and energy dissipation capacity. Plastic and compact sections are therefore preferred over semi-compact and slender sections. Like height to width ratio, which are giving the plastic and compact property of sections, that sections we have to choose. And other control parameters also, that is the slenderness ratio and axial load ratio of members, these are also required for energy dissipation. For earthquake, we need to design our building such that the mass of the structure is less to some extent. Earthquake forces is proportional to mass. Whatever be the mass is greater, it will attract more the earthquake force. So in this regard, we can see that for RCC structures also resist earthquake, but in compared to for a same RCC building, if we design it for it to a steel building, steel buildings will have lesser load compared to concrete. So it will attract lesser earthquake force for a same earthquake frequency. And we also need to be sure that the structure has some symmetry and regularity in the planning, in vertical and in plan direction and also in vertical direction. Because non-symmetric and torsionally unbalanced buildings are prone to earthquake damage due to coupled lateral torsional movement, producing non-uniform displacement demands in the building elements and concentration of stresses and forces on structural member. Also, we have to be sure that strength and overstrength capacity of a building. This overstrength theory I will explain in the later slides. Also, already it is explained the ductility, why it is required. Ductility is the extent to which a material or a structure can undergo large deformation without failing. When load is increased in the member, it will deform much before failing, so that the people in the buildings or the anything in the buildings that we can get time for evacuate and we can resist the failure. The term is used in earthquake engineering to designate how well a building will endure large lateral displacement imposed by ground shaking. Here, I will all these things are explained in IS 1893/2016, just to point out that we have to remember all these provisions while planning for a building. Like irregularities are not expected for a general building design. Like in the first figure, it is a torsional irregularity. It is showing some parameters are there that to what extent it should be there or not. In should not be any re-entrant corners, though we know that in our present scenario we have lot of these irregular shapes and buildings, because we have to prepare the good aesthetics of our buildings. So sometimes we cannot avoid all this, but at least we should remember while planning of any building. And when code is giving that guideline, we have to be ensured that it is followed in this way. Some irregularities in cutouts and floor slabs, that is also been pointed out in IS 1893/2016. Here again some provisions for irregularities in plan dimensions. Actually, we have to distribute all the masses in a uniform way throughout the building, and also we have to choose the lateral load resisting system in such a way that the CG of the lateral load resisting system is almost coinciding with the CG of the mass, so that there is no eccentricity. In practically, it is not possible in many times. For that also, code has given some guideline that what extent the amount of eccentricity we can take. That I will explain in the later slide. Here again some provisions for mass irregularity, stiffness irregularity, and some vertical irregularity in a geometrical form. Like in 4A figure, you can see that there is a stiffness. We have to ensure that there is no variation of stiffness, so that it will create the soft story failure of a stiffness of a lower floor lesser than the stiffness of upper floor. In this case, the lower floor will fail first before the than the upper floor. So all the building can collapse if the ground story stiffness is not higher than the upper floors. There should not be any mass irregularity also. We will try to distribute the mass as uniform as possible. Lateral, here you have seen that in elevation, in the second picture, there is floating columns. So floating columns should be avoided. In some building, floating columns are provided, maybe due to some restrictions of architectural, but when we are providing that floating, first it should be avoided. Even when it cannot be avoided, we should be design the floor from where started, that floor, and maybe we will choose the adjacent floor if we can provide a truss system like things between two floors, and these two floors, the space between these two floors can be accessed for the service lines. In some high-rise building, this system is followed when this floating columns cannot be avoided due to architectural planning. Here, some theory behind the earthquake load analysis. It is given as the earthquake forces. It is a external force acting on the structures. It is causing the vibration in the structure, and the property of inertia of the structural members, and the damping force, that is there is some friction or any lateral load resisting system it is providing. That force, all these forces are in a what we say, in a equilibrium form. It should be in a equilibrium form. That external force, what is acting on the structures, it should be resisted by the inertia force and damping force of the structures. So that is modeled in a that model is shown in this picture. First one is for single degree of freedom systems, that is the vibration is only in one direction only. And in the second picture, it is multi-degree of freedom systems. And these things are analyzed following the principle of structural dynamics. Here, a schematic diagram, that is mass of the structure is lumped as top, it is showing as M, and the ground acceleration, that is UG, and the structure is displaced due to this vibration. That relative displacement between ground and the mass, that is the value of U, and UG is ground displacement. And now we are writing the equation of motion, that is M U dot. U dot means the acceleration. Cu, that is U dot, that is the velocity. C is the damping force, and K is stiffness into the displacement. So all this together should be resisting the earthquake force. And we use eigenvalue problem to solve the equation of motion using in earthquake analysis. Oh, this system, I think it is repeating. By mistake, the slide has been repeated. Already we have explained that we have to ensure the structure to design for the earthquake, for moderate earthquake, the structure should be elastic enough in its return period. And for severe earthquake, we have to allow some damages, but not to collapse. We have to ensure the health and safety for public, and not only the reducing the financial losses. Here, how we analyze the structure. In the linear elastic line, force is increasing and creating the displacement delta y, Fy creating the displacement, maximum displacement delta y. When the reverse direction force is acting due to earthquake, the member which was loaded up to Fy amount, then it is going to reduce by the same rate. Fy is decreasing, and the displacement is in the negative directions. So the area covered by the cycle, that is the energy in earthquake which lateral resisting system is dissipating. And what is ductility? If the here the curve is showing fully linear for linear elastic curve, and then it is getting flattened. Actually, it is not fully flattened just after the point of yielding, but for simplification, it is shown as fully flat. So delta max is the maximum deflection that the structure will be allowed before collapse, and delta y is the displacement at yield point. So our structure, we made ductile so that we get a ductility value delta max by delta y. So that is the ductility property of a structure. How to design for an earthquake load? First, for earthquake load, three things we have to keep in mind. Only the material we will choose, it is not sufficient. Only to choose the lateral load resisting system sufficient, it is not very sufficient. We have to also ensure the level of detailing which are useful for seismic analysis. So we have to depend ductility of the material, ductility of the lateral load resisting system, and the ductility of the connections in buildings. 4 types of ductility we have to ensure. Here you can see in the curves, restraint curves for his steel members. In the linear part, force versus displacement is linear. that is stress versus strain, is linear. At some point in the elastic point, it is reaching the elastic point. After that, it is downward. Then it is getting flattened and getting the upper yield point. So after yield point, the zone is plastic. After the lower yield point, up to the flat end is ending. Then it is getting strain hardening, like load is increasing, but the load, the strain is getting there in the member, and at some point it will fail. So our member will be, we will choose that is yielding, and it will not have the brittle property. It will not collapse suddenly. Then we have to be ensured that the section we have chosen, whether it is I section or hollow section or any other section, that is more ductile, resisting the designed earthquake forces which we are getting in a particular structure. Here you can see that when load is increased or member is getting subjected to any forces, that is bending moment, I section, for example, for I section, first the extreme fiber is getting stressed due to bending moment. In the elastic analysis, just getting the Fy in the extreme member, we will design our member based on that. But for plastic hinge, when the plastic hinge will form that extreme fiber stress, then it is, then the after this extreme fiber, then the next fiber will getting stressed to maximum yield point. Then simultaneously it will reach to the fiber at near to neutral axis. Then the form of square form will be there, that all the fibers in compression zone and in tension zone are in yield point. So at that point, the section is reached to plastic hinge point. Then the section may rotate. So that system we have to be ensured that our member will not collapse, will not fail, but it will form plastic hinge. Then we have to ensure another things. We will allow the yielding of whole section in tension and compression, but we will not allow the local buckling of any member. We have to give the section property based on that. Here you can see the flexural yielding, which we are saying that flexural yielding, axial yielding, and shear yielding, that is allowed, but connection failure is not allowed, because in steel members, in steel structure, if the connection fails, the whole structure will fail. So we have to be ensured that before the connections, the member will deform, member will get yielded, but this connection is strong enough to resist the forces. And then our system has to be ductile. Like for system to be ductile, in the figure you see in the left is general 2D frame is there. In this 2D frame, in the second picture, the red dot is the plastic hinge in the column point. And in the right hand picture, plastic hinge point are in the beam and also in the column. So our structure will be like that we have distributed ductility in a structure, not that we will design some members of a structure is ductile but not the other ones. So we have to distribute the ductility in the system. Another point we will have to analyze in the earthquake resistant structure, that is response reduction factor. Response reduction factor, what is that? That it is the indication of extent to which the energy is dissipated through inelastic deformation during an event of seismic excitation. In elastic analysis, the line is straight, that force versus displacement curve is straight. And what is the maximum displacement? It is there that displacement, for this displacement, the force causing this displacement, it is V elastic, and we design the structure corresponding to delta Y, that is in the yielding point delta Y. So it will be the V design. And what will be the R factor? That is the V elastic by V design. Like for the structure, we will before designing the structures, we are thinking that how much damage we can allow for a structure, because for maximum amount of earthquake, that severe earthquake, if we design the structure in a robust one, it may not be feasible for economic purpose. So we have to judge our give our judgment and design the structure according to response reduction factor. And it is depending on the framing system, material, everything. Code is giving some values for different moment frames and different braced frames, and for RC building different, and it is also different for steel building. Now, how to determine the lateral force of earthquake on structure? 1893 giving the provision to design the earthquake force, to quantify the earthquake forces. It is depending on some factor, that is design acceleration spectrum, that is AH. And the AH is maybe we are studying all this in our academic syllabuses, that is Z by 2, SA by G, R by I. That all factors are creating this design acceleration spectrum value. Z is for zone factor. We have 4 zones now to be considered in seismic design: 2, 3, 4, and 5. Importance factor depending on the building type. Response reduction factor depending on the building framing system, that is moment frame or brace frame. And the design acceleration coefficient, which is depending on the soil type, whether it is hard soil or loose soil, and it is also depending on the natural time period of the structure. Here you can see response reduction factor IS 1893. It is giving some factors. Why I have marked it red? Because in this webinar we are concentrating our presentation in steel building, so we have highlighted in this way. You can see that steel building with ordinary moment resisting frame, our response reduction factor is 3, and steel building with special moment resisting frame, that is factor 5. That means when our load is like some about value of V, we are reducing the value by 1/3 for a steel building with moment resisting frame, ordinary moment resisting frame, and the forces we are reducing by 1/5 for special moment resisting frame. That means for special moment resisting frame, it is the for more effective system for earthquake resistant structure, as a earthquake resistant structures. And same for some values are for braced frame, that building with ordinary braced frame, building with special braced frame, and building with eccentric braced frame. And some values of importance factors is also for the use of the building, for importance of the building. Like for residential or commercial building, it is giving 1.2 value, but other buildings like rail station, where damages and toll of lives may be greater for any collapses, so for that importance factor is 1.5. That is, we have to design for more earthquake forces. But other than general building, we can use the importance factor as 1. Here 2 SA by G curve. One is for spectrum of equivalent static method, which we will explain in the later slides. And second one is for response spectrum method. Design acceleration coefficient SA by G. Now, method of analysis for seismic loads. Code has specified 2 methods for earthquake load analysis. One is static analysis method and other is linear dynamic analysis method. Static analysis method is equivalent static method, and this is applicable for regular buildings less than 15 meter in seismic zone 2. But and also we have to see that whether the natural time period of the structure is less than 0.4 or not. And linear dynamic analysis method, it is not required for regular buildings less than 15 meter of seismic zone 2. In other zones, in seismic zone 3, 4, 5, we have to analyze the structure for linear dynamic analysis. And for linear dynamic analysis, there are two methods, that is response spectrum method, time history method, and time history or site specific method. Another is non-linear dynamic analysis. It is not included in the provision of IS 1893. In equivalent static method, this AH value is same as we have seen in the earlier slide, that is Z by 2 SA by G into SA by G by R by R. And minimum design lateral force, it is VB is equal to AH into seismic weight of the building. For seismic weight, we have after calculating the seismic weight, we have to distribute all the seismic weight to the respective after getting the seismic weight of the building, we have to distribute the seismic force to each floor depending on the formula, that is QI, which is depending on the individual weight of each floor and the height of the respective floor from the ground level. And in linear dynamic analysis, the structure is analyzed for a some vibration mode. Like structure is supposed to vibrate in different modes, like first mode of vibration, second mode of vibration, third, and many other modes. So all these modes are considered in linear dynamic analysis. Code has specified that design base shear calculated using linear dynamic analysis, that is VBD, should not be less than design base shear calculated using fundamental natural period TA, that is also calculated in equivalent lateral force method in VBS. Like VBD should be greater than VBS, and if the VBD less than VBS, the force response quantities shall be multiplied by the respective factors, that is VBS by VBD. And all the story shear, base reactions, all these forces will be multiplied in the same ratio. Another portion we have to which clause 6.4.3.1 is specifying, that is effective section properties of the property of the members. Here all the modal masses, how to calculate, generally all these things are very rigorous process. It is not done manually. All these inputs of some R values, zone factors, SA by G value, and the soil property we give in the any software we are using for analysis, and software is analyzing all these modal masses and giving us the final story shear and the member forces for this earthquake. Because this linear dynamic analysis is not really done by any manual analysis. Equivalent static method we can do manually, but it is little bit cumbersome because it is repetition. First we have to consider the fundamental natural period. We give the natural period respecting SA by G value. We get the first mode of vibration value. Then we have to keep it for second mode of vibrations. So all these modal compilations cannot be done manually. And I have just took the clause specifications of IS 1893, that clause 7.7.5.4, just to show you that these theories are behind the linear dynamic analysis. Here, the design acceleration spectrum for response spectrum method. The difference with the response spectrum of equivalent static method is that in equivalent static method, for zero natural period, still there is a value of SA by G, that is 2.5, is fixed for zero natural period. But here it is lesser than 2.5, and it is also increasing from 0 to when it is increasing the value. Design acceleration spectrum, it is also sometimes we use site specific design acceleration spectrum depending on the requirement of the structural design and the requirement of the project. And code has specified that when we are using number of modes in a direction, sum of modal masses which are contributing in the earthquake force generation, that 90% of total seismic mass is considered in modal masses. That is, after the software analysis, we can see from the output that all the modal masses in each mode, that total modal masses should be 90% of total seismic masses of the building. Another system we have to ensure that when we are designing the lateral load resisting system, the earthquake forces is finally getting transferred by lateral load resisting system. But how these forces will go to the lateral load resisting system? For that, the building floor need to act as a rigid diaphragm in lateral load resisting system, so that the force is transferred from one framing column to the other framing column or members through the building floor slabs. And it is possible when it is effective, mostly effective on when the building floor is acting as rigid floor. If it is not possible, if it is to some extent flexible, we have to check how much it is flexible. So code has guided us for this to flexibility of the floor diagram, to check the flexibility, that what value is allowed. That is, here in the figure, that delta middle of that displacement of the floor should be greater than 1.2 delta average. So we are allowing that flexibility of the diaphragm that we can consider in lateral load resisting system designing. One point we have to be ensured, design eccentricity. In the analysis of structure, in calculating the structures, while giving input, we have to give that eccentricity value. What is eccentricity? It is the distance between the center of mass and center of the resisting system, like where we are providing the braced frames, where we are providing the any shear walls or any other load resisting system. If we are designing at moment resisting, we are calculating the CG of the lateral load resisting system, that should be coincide to the most extent possible with the eccentricity in the center of gravity of the mass, so that there is no eccentricity. What the force is acting is getting resisted fully. Even if there is eccentricity, that allowable value is given in the code, that is 1.5 ESI plus 0.05 BI. That 0.05 value is for the accidental eccentricity. In linear time history method, in the response spectrum method, we are having the code given response spectrum for some natural time period of vibrations. But when linear time history method we are applying, like it is specified by the client that we have to take that method or not. Like for linear time history method, we have to take some previous data of earthquakes, which we can get from the institutes which are recording the data for earthquake. So we have to use average. It is recommended that at least use 3 previous ground motion, and we take the average of the ground motion. Then we take that SAYG value from that curve and we match with the design spectra. We consider the 5% damping, and then we analyze the structures with finally available response spectra. That is the average of 3 ground motions of earlier earthquakes recorded. Some drift requirement is specified in the code. Why it is required? In after the earthquake, we always see some tilting of the structures. Even there is no collapse, it has been tilted. So for that, it is getting damage also when the building getting tilted and fell on the other buildings. So for that, the pounding effect that is should be restricted. What is pounding effect? That is the building simply mean it is the collision of two buildings due to earthquake load, and it happens due to irregular response of the adjacent floors of the buildings during the earthquake. So to resist that, when we are designing some different unit of a building or any separate two buildings, some separation should be there. That is the value of R1 delta 1 plus R2 delta 2. R1 is the R1 delta 1 is the first building for the, and R2 delta 2 is the corresponding response spectrum value and the displacement value of the second building. And left one, it is mentioned as story drift limitation. So for story drift, that respective story displacement should be like that. That delta 1 should be delta 1 less than should be the 0.004 h1 less than 0.004 of that height of that particular floor. And delta codal provisions to guide us that how much we should allow for the sway of the floors. That is delta 1, which is the sway of first floor, should be less than the amount of 0.004 multiplied by the height of that floor to floor height of that floor level, and the corresponding displacement of the second floor should be the delta 2 minus delta 1. That relative displacements should be limited to 0.004 times of height of that particular floor. And other than designing the lateral load resisting systems, after designing, which is we are designing for earthquake, other than this, all other members which are not acting for the earthquake load resisting, that members also should be the required bending moment and shear force capacity for all the design forces it is acting. And it is mentioned in the clause 7.11.1, and these forces should be delta multiplied by the response spectrum value of that particular building, and it is specified to design like in this system, in this way, in zone 3, 4 and 5. So here is some in a short form what clauses we have to remember in and follow for the earthquake load resisting system. That horizontal diaphragm design, some explanation we have seen in the earlier slide, that is clause 7.4 to follow the 7.6.4 guideline. Design and horizontal vertical loads, the torsion requirement, that is the eccentricity part, structural irregularity part, that is table 5 and 6. We have to see the projection part also while in the planning part in the building in the starting of the building, and addition to existing structures that is mentioned in 6.1.7, and is there any change in occupancy that we have to consider in while analysis of the building. In today's presentations, we are restricted in the lateral load resisting system only, but there is some clauses in foundation design for the earthquake load analysis. That is, we have to follow the clause number 7.12.1, and for compound walls, there is some clause in 7.12.3, and the connection between the parts, that also is very relevant points in this system design, that is mentioned in 7.12.4, because sometimes corridors or connecting parts fail in the earthquakes because it is not designed to the for its full capacity. Now I will explain some points to design the steel framed building and some clauses in section 12 of IS 800. As we know that all the horizontal load is resisting by the vertical framings, and vertical framings in maybe in the form of only framing moment or base frames, or in combination of frames and shear walls, and maybe in some moments and shear walls only, not the framing. Moment frames, there are two types of moment frame: ordinary moment resisting frames, special moment resisting frames, and there are four types of brace frame, that is ordinary concentrically braced frame, specially concentrically braced frame, eccentrically braced frame, and buckling braced frames. Special moment frames. So here beams and columns with the moment resisting connections. It resists the forces by flexure and shear in beams and columns. And in this moment frame design, we have to always use the principle that we will design the beam in such a way that the plastic hinge form in the beam first, not even in columns. And we will follow the theory strong column, weak beam to resist the earthquake forces. Here in the figure, you can see that we are forcing the beam to get the plastic hinge rotation point first before the column. We have to ensure how we can ensure. Sometimes we will ensure the hinge formation to be in the beam, reducing the beam flange section at that point, as the beam flange is taking the moment load. So we can reduce the beam flange so that it will reach the plastic moment capacity. When it will reach the plastic moment capacity of that section, it will go to it will act as a hinge point. But at the same point, the other sections adjacent to the members and the columns will be designed more than the capacity of that plastic hinge points, so that all other sections doesn't collapse or doesn't fail before the plastic hinge formation. In this figure, it can be understood in a better way. In the top, it is in plan. You can see that the point in the location of 1.1, the flange width is reduced. It is cut in such a way that this portion we are forcing it to get the hinge formation first. When the hinge formation is in the beam, the floor above it can crack, but it will not fail the whole structural frame of the building. And the same concept we have to follow for all the beams for the moment frame using to resist the lateral load resisting system. We will allow all the beam part of the frame to get hinged first, not in the column. Here, the strong column weak beam theory is explained in figure. In the left figure, all the beam are getting the plastic hinge formation, so the frame can sway, but it will not collapse. But in the right figure, when the column will get the hinge point, after the hinge point formation, the frame get collapsed without any um, without any indication. And behavior of frames, here some different kind of frames are shown, that is diagonal cross bracing, chevron bracing, and eccentric bracing. Concentrically braced frame, it is not that much ductile compared to moment resisting frames, but again it is depending that how much important structure and in which zone we are designing the structure. So in considering all these factors, we will choose the structural load resisting system for earthquake. These frames is not as ductile as moment frame, but we can use it in seismic zone 2 and 3. Concentrically braced frame, it is much effective than concentrically braced frame, as we can have a link between the in the framing members, that we can use the link to fail first before the all other members in the framing, so that the framing is getting ductile, that is it is deforming first before collapsing. And in this eccentrically braced frame, beam, columns, and bracing are connections are designed for overstrength than the link. The link will get fail first, but not the all other members. Some pictures of failures in the concentric braced frame, just to show you the how it is acting and fails. Ordinary moment resisting frames, as per clause 12.0 of IS 800 2007, it is not allowed in zone 3, 4, and 5, and connections are as per clause 12.10.2. That is, connections are permitted to be rigid or semi-rigid moment connection, and it satisfy all the criteria of 12.10.1. Special moment resisting frame. For special moment resisting frames, R value is 5 as mentioned in 1893, and it is detailed and proportioned for large inelastic drift. Here you can see that all the plastic hinge point are allowed to form in beam only. And here the design should be such that plastic moment of column and beam should be such that sigma MPC by sigma MPB should be greater than equal to 1.2. That is, column moment is always greater than the beam moment capacity. That's why the moment the beam getting the plastic hinge point first. And also the shear buckling checking is done for the panel zone. Now it is showing the concentrically braced frame. In this framing, beam, columns, and bracings are arranged to form a vertical truss, and it resists the earthquake forces by truss action. And here we allow the bracing member to fail first before the other members of the frame, that is beam and column. And the bracing yields in tension first before it buckles in compression, so that the structure should not collapse. Ordinary moment frames, some provisional code provisions are there that for ordinary braced frame, concentrically braced frames, slender sections are not allowed, and axial compressions, which we will design, the section will be provided for axial compression, it should be less than the 0.8 of design forces, and slenderness should not be greater than 120. As we are saying that it should yield in tension first, that's why this all slenderness ratio and this axial compression value is mentioned. That is, P design is the compressive force, and this axial compression is 0.8 times of P design. And for connections, connection part should be designed as 1.2 times of FYAG for tension, and also the connection member should be designed for the 1.2 times of plastic moment of the beam section. And connections are also checked for net tensile rupture, block shear, and gusset should be checked for out of plane buckling. And for specially concentrically braced frame, the connection design guideline is as per clause 12.8 of IS 800, and response reduction factor for this particular frame is 4.5, and this frame is allowed in all the zones. That is, 2 is always allowed, 3, 4, 5 we can choose this framing for the lateral load resisting system. And for this cross bracings in the specially concentrically braced frame, we have to use the plastic section always, and minimum 250 B steel, and the same theory, that is the P required for designing should be less than P design, as we have seen earlier that in concentrically braced frame it was 0.8 times P design, it was the limiting value, but here it is the P design is a limiting value. And also the slenderness value also it is allowed to be greater, that is less than 160. And when we are we are designing the member for compression, at the same time we have to design it for tensile bracing, as the load is reversing. When the member is acting for tension, maybe it will acting for tension compressions at the next time. So for tensile braces also we have to design the member for 30 to 70% of the load. And connection is same as ordinary concentric bracing, that is the plastic moment capacity has to be considered, and the connection should be designed for 1.2 times of plastic moment of the member. Here are some pictures showing that in eccentrically braced frame how we can use the link for the fuse element. Like in the left side, the link, the vertical link has been used so that the bracing member doesn't fail before the link fails. And in the right picture, the horizontal link has been shown, and these links are provided some smaller section than the adjacent two sections, and some bolting is done between the link member and the adjacent members with the links, so that when it is hinge form is there, it can move between the bolts. And same theory is for the vertical links also. In this two system, the bracing will not fail, but the link can fail. That is, we are allowing and assume the structure that to behave in earthquake load. There is some more figures just to understand in a better way. Concentric bracing, then the buckling bracing and link beam in the eccentrically. Now, for steel structure, as this presentation is specifically concentrating on steel design for earthquake, So we will mention that always steel is strong material as a ductile for its ductile property, which is very much used in seismic design of any steel structure. And we know steel is strong in tension, but when we design for some compressive value, it will buckle before it fails. And steel members are produced in high quality control with high quality control, and steel structures having flexibility and lower mass, which will attract lesser earthquake forces. And also we can use the capacity design method, and we can sequence the plastic hinge formation, that we can ensure that the beam get the formation of plastic hinge first. All the beams of any framing system get the plastic hinge first, then the columns, so that it will not collapse. Now, behavior of some steel section, that is I section and hollow sections, just to make some understanding that behavior of I section under seismic load. Here you can see that the hysteric curve of I section in cyclic loading, that is in load reversal, it in a widespread area is in between the cycle. That means there is amount of energy, that is work done by the member for dissipating this earthquake forces energy, it is more. So I section have good ductility property, and it fails in local buckling of flanges first. Sometimes cracks is followed by the sometimes it is followed by the initiation of cracks at the flange wave junction, but we can design the connections in such way that it will be avoided. Some more theory of response of I sections under seismic load, that for local buckling, strength of the members is reduced, and there is pinching of hysteretic curve after crack initiation can be observed. But for compact sections, this tendency of cracking increases. With rigid connections, compact section may not provide the required rotation. So we have to keep it in mind. This hollow section also having good ductility property, as it is hot rolled and fabricated with 4 plates welded together. These sections have low width thickness ratio compared to sections used in breech piers. And these sections was scored over the I section due to the fact there are no outstand, and it consequently the ultimate strength are higher, and post buckling performance is also better. And as you have seen, that hysteretic loop shape is similar to that of I section. And in case of higher width to thickness ratio, the section degradation in strength and cycle is desirable. So we will keep it in mind that lesser as we can keep. And the failure of this section is by inward buckling of the flanges, followed by the outward buckling of the wave plates. Here, how it is failure is there for earthquake loaded in circular hollow section. Unlike RHS and CHS are more difficult to connect to I sections of beam, and it may require elaborate external stiffeners to achieve a ductile connection. Connections is sometimes is really problem for hollow section connections, which are easy for I section. And it can be seen from load diagram figure that hysteretic loops are more rounded and have negative slopes in the plastic region. And this is due to the type of local buckling and the way it spreads around the circumference. When a CH section is subjected to bending in one direction, the part of other directions under compressions develop local buckling outwards. As the bending moment is increased, the local buckling spreads along the circumference of the tube, since there is no waves to arrest the spread like in RE section. If a bending moment is applied in the opposite directions, a similar local buckling develops and finally merges with the previously developed local buckling to form what is known as ring type local buckling. So sometimes we see that CHS sections fail in earthquake loading. Some more theory of seismic behavior of circular section, that the formation of ring type local buckling not only gives smaller ductility values for CHS as compared to RHS, but also causes progressive collapse under moderate but long duration earthquakes. This is because when cycled at low amplitude, the side which buckles first tend to have smaller maximum strength as compared to the opposite side. As a result, the deformations on that side increases progressively, leading to collapse. Here we can see the failure mode of a concrete filled RHS, and concrete is in the confined state, local buckling is delayed in RHS. So it is an effective members for earthquake. Here we have I have just shown some connections which are used in the moment connections for earthquake load analysis. Just to show some pictures how the connection is done and how it fails, how the beam has been failed in the buckling failure, and sometimes weld may fail due to its brittleness. So we have to be very careful for designing the weld for connection. So this is all about some theories and principles behind the earthquake analysis. There are so many things, maybe it has been not covered in the presentations, but still I have tried to explain some basic theories in earthquake resistant design. And thank you for your listening.
Thank you, madam. I think it was a wonderful explanation given on the earthquake resistant design. I think, madam, you have highlighted points on the general philosophy of design, then the shape of the building, then the provisions in IS 1893-2016. Then you have also explained the behavior of frames with bracings, various kinds of bracings, then behavior of individual structural elements. Madam, we have a few questions on this. Madam, how to design how to do analysis and design of this concrete filled tube structures?
So let me be very frank. For concrete
madam,
filled tube,
madam, you can exit from this presentation mode.
Okay. Stop sharing. I am doing.
Yeah.
So is it okay now?
Yeah, okay, madam. You can switch on the video.
Okay. So let me be just very frank that design of concrete filled tubes, I have not done in practical design. Some literatures are there in the publications of CDECT, that is following the foreign code based on Eurocode. But practically, I have not designed any structures with concrete filled tubes.
Okay.
Still, we are studying on these subjects. So maybe we will give some informations after some time.
Not an issue, madam. Not an issue. Madam, you said in this moment resisting frame, we will be reducing the.
It is good that just to mention, sir, when we are filling the tube with concretes, actually the steel section, outer steel sections is taking the moment, okay, and inside concrete is taking the much of compression. So in this way it is more effective than any other section, that we are considering the compressive force of full concrete and the moment capacity of steel flanges outwards. So in general, it is very much effective. But the theory of whole design procedure, the clauses and everything, that I am not very sure and cannot tell.
Okay, madam. I understand, madam.
It is explained in CDECT publications of.
Okay. And madam, you said in the moment resisting frames, you will be reducing the flange cross section. We are going to cut the section at the top flange. Now, how do we really ensure that in analysis?
Hmm.
Madam,
No, in analysis, when we are giving the section, in analysis, when in the software, like when we are putting the sections, there is not provisions to keep different section properties at different point. But while designing, when we are getting all the forces, that moment diagrams we are getting for the particular member, and we choose the sections and where the plastic hinges we will allow. It is we will decide that time only, but in the analysis part, it is not possible to give that different property of a beam members in the software, because in beam member only one section property we can give. Am I clear, sir? Am I audible, sir?
yeah, madam, there was some disturbance. Yeah, okay, madam. I think, madam, in that one more thing regarding this plastic hinge in special moment resisting frames, the plastic hinge formation occurs in the base plate, I mean base of the column. In such cases, how to ensure this drift? Because code has its own limitations on the limits on the drift. If even after having such drift limits, can we? Is it really ensure that the plastic hinges are going to form at the base?
No, we will not allow the plastic hinges in the
Yeah.
column. We will ensure that plastic hinge forms to beam only.
Okay. In special
Because if we allow the plastic hinge formations in the columns, in column sections may fail and it will create collapse. And maybe when special moment resisting frames we are choosing, after all the beam members are subjected to first plastic hinge is formed, then only we will allow the plastic hinge at the column base, not before that. Am I audible, sir?
hello, madam.
Hello?
Can you hear me, madam?
Yes, I can hear
Yeah.
you.
That is another thing, madam. And madam, one general question. We have this always frequent upgradation of the codes. Then we might have designed the structures for the previous code. In such situation, will those buildings comply with the revision that is made in the code? How to ensure that, madam?
Okay, you are telling the buildings which we have designed in the earlier provision of
Yes, madam.
1893, all the revised
To,
some clauses of 1893.
yes, madam.
That
2000,
is your question.
yeah, 2002 there will be some clauses, and 2016 there will be upgradation in the clauses. And in such cases, how to manage?
then sir, I have to
Yeah.
compare, but at this moment I am not able to give that it how to be be ensured. Maybe in some portions we have to strengthen the structure. If retrofitting is possible, we have to be sure on that, and maybe we have to go through the earlier design, that whether the member section property and everything are really matching with the new provisions. If not, if there is any provision that we can do some retrofitting of structures, even in RCC or in RCC, retrofitting is possible.
Okay, madam.
But for that, I really, that questions is really, I have not think in this way. I have to compare the previous 2002 version and this 2016 versions, that what are the basic changes and what the effects it is causing in the earlier design structures.
Okay, madam. Okay, now can I request Pavitra to take up the question and answer session from participants?
Yes, sir. Like RCC structural elements, what are the minimum size section recommended for structural steel elements as per Indian or international seismic codes? I'll repeat the question once again.
What is your question, madam?
Like RCC structural elements, what are the minimum size
Yes.
or section recommended as per Indian or international seismic codes for steel elements?
For RCC or still you are actually
Madam,
the minimum
madam, maybe the
dimension
question is dimensions, regarding the dimensions.
guided
Yes, ma'am. Tell me.
The section dimension mainly guided by the slenderness ratio of the members. Okay, so we have to check for the slenderness ratio of the members. For earthquake also, we need to check the slenderness ratio. Like for bracing member, for all the provisions are there, different clauses in 800, the section 12, that what will be the slenderness ratio of the member. So that will guide the minimum dimensions of any member. Because for seismic, either in RCC or steel, it will be designed in a bracing form or in a moment frame that will be subjected to buckling. It will depend on the slenderness ratio.
Okay, madam. One more question. What is the technology behind Japanese?
The particular one dimension. What is the technology?
What is the technology behind Japanese building built by bearing technology?
That, frankly speaking, that is, I am not very much clear about this concept.
Okay. Okay, sir. That's all from my side.
Okay, madam. I think you have given us very good information regarding the design of steel structures and using seismic codes. And I think on behalf of VIVEKANANDA Institute of Technology, I wholeheartedly thank you, madam, for giving such an insightful lecture. I also thank the participants for being part of this lecture. Now I request A.K. Samantha sir for his final remarks.
Sir, thank you very much. Just I was listening to Nibedita's lecture. Actually, earthquake resistance, to my, though I am not civil engineer, but to my understanding, it is quite complex behavior, because earthquake itself is unpredictable incident. So during that incident, exactly how structure will behave, it is very difficult to visualize. However, I think she has tried her best to deliver the concept or to make you understand the concept. But still, we are having. I think she was talking about the behavior of steel structure. But I think Madam was asking about the what is the minimum section used in concrete structure exactly. The lecture was not containing concrete structure, even that to my understanding, it was not containing the composite structure. But anyway, and you know, in concrete structure only we are using rebar, not much that structural section, angle beam, channel plates, etc., or tubular section. But steel structure, we are having number of sections, and this is rolled with different quality, different dimension, different strength level. So, to my understanding, it may pose very a little difficulty in designing the steel structure, this earthquake resistance. But one is definitely the plus point of the steel structure is normally due to its strong ductility, it normally bend but does not break. So whenever we have experienced any earthquake, as a natural calamity, we have observed that steel structure has survived better compared to concrete structure because concrete is basically a brittle material. So once its strength goes or any, and you know the concrete has is strong in compression but very weak in tension. Rather, that steel is very strong in tension, but even in compression, it behaves in a better way. It buckles but does not break it. So that's why most of the our entity, including the vehicles also, that motor vehicles, transporting vehicles, everything is made of steel, not other. Just because of the two important properties of the steel. This one is that ductility, another is that impact strength. Because during accident it absorbs lot of energy. So that's why steel structure give the better advantage to the user. But again, as usual, concrete is very popular, and not only that, on direct cost basis, it is cheaper. Things will go on, research is going on, code will be updated, and we have to learn it. It is a very, I think, very important and very complex subject in structural engineering. But anyway, I must thank Nibedita. She has tried her best. Even I could understand many things whatever she was telling, though I don't understand much the structural and design aspect, but still it was convincing for me. I think those who are from the civil and structural background, they have understood and they have learned a lot. With this, my thanks to your college, your participant, as well as my colleague Nibedita. So if you permit, we should break this session. And now,
Definitely, sir. Definitely, I think whatever the words you said is really a highly valued thing, sir. And I think this lecture will definitely have a relation to the next lecture, which is in the afternoon session.
yeah, yeah,
Uh,
yeah,
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 definitely there is a relevance,
yeah,
and much more constructional aspects can also be known. I think in
yeah.
the afternoon lecture.
And I
Uh,
can tell you the question you are thinking now. You
yeah.
may pose this question to Mr. Santilal Jain because recently he has designed 100-story building in Mumbai and he has constructed also. So he is having large experience as of practical aspect.
Yes.
So this question may be asked him also.
Yeah. Yeah.
Okay, but
Yes.
anyway, sir, thank you very much. I
Thank you so
think
much, sir.
your participant has got some benefit out of this
Definitely, sir.
lecture.
Definitely, sir. Definitely.
Okay, sir, thank you.
Thank you, sir. And I request all the participants to join the next session at 2 o'clock.
Thank
Thank
you.
you so much.
Thank you.
Thank you, all of you.